So far, all semester long, we've been finding derivatives of given functions. Many of the problems in calculus actually involve doing the reverse. Given the derivative, find the original function, which is called the antiderivative. The process of finding the antiderivative is called integration. The function found from the integration process is called the indefinite integral. The notation that we use to show that we need to find the antiderivative is this kind of a curly Q looking almost S symbol. And then we have f of x and dx. You'll have the function given to you, and at the end it'll say dx or du or dt, just depending on what the variable is. The integral symbol itself is like a square root or a logarithm or a limit. You have to be doing the integral of something. If you just write the integral symbol with nothing after it, it doesn't mean anything at all. For some basic practice on finding antiderivatives, on example 1, I have given you various functions, and we are going to find the antiderivative for them. So think about if you were given a function and told this is a derivative, and the function you were given was 3. What would you have taken the derivative of to get an answer of 3? If my derivative was 3, then my original function had to be 3x. Now, what we do on these, and part of why they are called indefinite integrals, is that we have to put a plus c on the end of that, because it could have been 3x plus 5, or it could have been 3x minus 20. There could have been some constant on the end that we have no idea what it was, and its derivative was 0, and therefore doesn't show. So when you are writing the answers for indefinite integrals, you must always write plus c at the end. Moving on to the next function. If I have a function that I know is a derivative, then what was it originally? If it's 2x, well, then it had to have been x squared. Don't forget to write plus c. If my derivative is 3x squared, then my original function must have been x to the third plus c. Notice what we're doing on our variables. We are adding 1 to the power that we had originally. And that makes sense because when we found the derivative, we subtracted 1 to get the new power. Looking at the last one, our function is x to the third. That's a derivative. So that means that originally it was an x to the fourth. But when I dropped that 4 times the coefficient on the front, my answer became a 1. So that means that I had to either have a 1/4 x to the fourth, or you can also write that as x to the fourth over 4. They mean exactly the same thing, plus c. These two are exactly the same thing. We're going to begin looking at some of the basic integration rules. The first one is that if you are doing the integral of k dx, that will equal kx plus c, where k is a constant. For example, if you had the integral of 5 dx, that will equal 5x plus c. If your derivative equals 5, we know that the original function had to be 5x, and we must always write the plus c. On our second rule, if you have the integral of k, a constant, times a function, dx, you can pull the constant out front, the coefficient out front, and just keep it. So if we had something like the integral of 5 times the function of x to the 7th dx, we can pull that 5 out to the front and do the integral of the x to the 7th dx. Rule 3 is telling us that if we have two terms being added or subtracted that we are doing the integral of, we can split them into two separate integrals and do each one individually. And this goes right along with doing derivatives. When we had terms that were added or subtracted, we just did the derivative of each individual term. Same thing here. If we have an integral of terms that are being added or subtracted, we just do the integral of each individual term. Rule 4 is our basic rule for how we are going to integrate individual terms. If you are doing the integral of x to the n dx, to find its antiderivative, you add 1 to the current power and then divide by that new power of n plus 1. In order for this to work, your n cannot be -1. If you think about that, if it was -1, we would have a 0 in the denominator, and we can't have that. Now think about what we did to find derivatives. We dropped the old power to the front and multiplied it times our x, and then we went down by 1 to find the new power. Here we add 1 to find the new power and divide by. So we're doing the reverse of what we did on derivatives. So for example, the integral of x to the 6th dx. We're going to add 1, make it x to the 7th, put it over that new power of 7, and write plus c. If we had the integral of x to the 10th dx, we're going to add 1, put it over that new power, and then plus c. You can always check yourself by doing the derivative. We can still use this rule even if our power is negative. If we have the integral of x to the -4 dx, adding 1 would put us at -3, and then we put it over that new power plus c. Let's put our integration rules into practice. On example 2, we're going to find the indefinite integrals. And a is the integral of 5 dx. If we have done the derivative and the derivative is 5, then the integral has to be 5x plus c. On b, we have the integral of dy. The trick on this one is recognizing that there is a hidden 1 in here. What would the integral of 1 be? It would be 1x plus c. On c, we are just going to use the power rule for integration. Our rule says that you add 1 to the power. 2/5 plus 1 or 2/5 plus 5/5 will give us 7/5, which we have to put over that new power now. Don't forget your plus c. We cannot leave it in this form. And remember that dividing by a fraction is the same thing as multiplying by the reciprocal. So this would become 5/7 u to the 7/5 plus c. On D, what you need to do before you do the power rule is rewrite this by pulling the variable up to the numerator. So you would rewrite this as 6x to the negative 3 dx. Well, that coefficient we can just pull out in front of the integral symbol. And so now we have 6 times the integral of x to the negative 3 dx. Our rule says just keep the coefficient. Now add 1, so you get a new power of negative 2 over negative 2 plus c. We can simplify this 6 over negative 2 and get negative 3x to the negative 2 plus c. And that would be fine for me to write that as an answer. But just know that you could also write this as negative 3 over x to the positive 2 plus c. Either answer is fine. On example E, we have the integral of the function 9x squared plus 6x plus 7 dx. When you look at this, because this is terms that are added or subtracted, our integration rules say that we can separate this into individual integrals. And then we have another integration rule that says if you have a coefficient, you can pull it out front of the integration symbol. Now, this last term is the integral of a constant, so you're not going to pull that out front. Now we can do our integration rule where we add 1 and put it over the new power. When you do this, you keep the coefficient out front. So we keep the 9. Now do the power rule for integration where you're going to add 1, put it over the new power. Plus, on the second term, keep the coefficient. Our function is x, so we're going to add 1, make it x squared, put it over the new power. Plus, the antiderivative of 7 is 7x plus c. This simplifies in the first term to be 3x cubed. In the second term, 3x squared plus 7x plus c. These two steps where we used the integration rules do not need to be written out. You can go straight to doing the integral of each individual term. We would have gotten exactly the same thing, and it saves us a lot of writing. For example, F, we have the integral of the function 8x to the 5th plus 2 over x to the 4th minus 6 over the 6th root of x, and that is times dx. One thing I haven't talked about yet is what this dx is on here for. That's on there just to tell you that everything in front of it is a derivative. It's just part of the notation that we use to show us that we are doing integration. On this problem, before we do the integral, we need to rewrite the second and the third terms. Our power rule only works when the x is in the numerator, and the second and third terms have the x in the denominator. So we are first going to rewrite this. The first term will stay the same. The second term, remember, when you move a power from the denominator to the numerator, it changes the sign of the power. So the second term will become 2x to the negative 4. And then the third term, we have the 6 already in the numerator, and we need to recognize that that 6th root of x in the denominator is the same thing as x to the 1/6. So when we move it to the numerator, it will become x to the negative 1/6 power. And all of this is already a derivative, so we write dx at the end. Now, each of these terms is in the correct form, so we can do the add 1, put it over the new power rule for integration. So our first term, we keep the coefficient. Adding 1 to the power gives us x to the 6th, put it over the new power of 6. Plus, keep the coefficient of 2. Add 1, you're going to get x to the negative 3, put it over the new power of negative 3. Minus, keep the coefficient of 6. We need to add 1 to negative 1/6. So think of this as being negative 1/6 plus 6/6, which is going to give us positive 5/6. And then put that over this new power of 5/6. Don't forget plus c. Now we need to simplify. In our first term, we have 8/6, so we're going to simplify that to become 4/3 x to the 6th. 2 over negative 3 becomes negative 2/3 x to the negative 3 power, minus, on this last term, we need to multiply by the reciprocal of the denominator. So we're going to have 6 times 6/5 x to the 5/6 power plus c. First term, we're not going to change. It's still 4/3 x to the 6th. You may leave the second term as it's already written, or you could make the power positive by making it 2/3x to the 3rd. Either one is fine. It doesn't matter to me. On the last term, we're going to take 6 times 6/5 and get minus 36/5 times x to the 5/6 power plus c. And that is the answer for this one. On example G, we have the integral of the function x minus 5 over x to the 4th dx. For what we know how to do right now in integration, we cannot do anything with this because it's written as a fraction. We need to do a rewrite so that we have individual terms with x's raised to powers. So we're going to be doing some algebra here. What we need to recognize is that fraction rules let me split this single fraction into 2 fractions with the same denominator. So I would have x over x to the 4th minus 5 over x to the 4th. And that whole thing is a derivative, so we have to put dx at the end. That first term of x over x to the 4th simplifies to be 1 over x to the 3rd minus 5 over x to the 4th. And the whole thing is derivative, so times dx. Before we can use our integration rules, our variables need to be in the numerator. So we're going to rewrite the first term as x to the negative 3. The second term will be minus 5x to the negative 4, and that is all dx. Now we have 2 individual terms with powers of x. We can use our integration rules. So now, on the first term, we're going to add 1, which will put us at x to the negative 2, put it over that new power of negative 2. Minus, on the second term, keep the 5. Add 1, you're going to get x to the negative 3 over negative 3 plus c. Your first term will then become negative 1 over 2x to the positive 2 if you want to move it back. You can leave it as x to the negative 2 in the numerator. Either way is fine. For the second term, it's already negative, and then we have a negative in the denominator, so it's going to become positive 5 over, putting the variable back in the denominator to become positive, 3x to the positive 3 plus c. Now we're going to look at techniques for finding antiderivatives for more complicated functions. We're going to use what's called the general power rule, and what we're going to be using this for are functions that we would have used the chain rule to find the derivative. Our general power rule says if u is a differentiable function of x, then the integral of u to the power times du dx, that means the derivative of the u, where the variable is x, equals u to the n plus 1 over n plus 1 plus c, and n cannot equal negative 1 because that gives us a 0 in our denominator. An example of what I'm talking about with this general power rule, for example 3a, we are asked to find the integral of the function x squared plus 3 to the third power times 2x dx. When you look at the fact that we have a quantity to a power here, this is what we're looking for right now. We would have had to do the chain rule to get a derivative of that. And when you look at the 2x, that is the derivative of the inside part. This integral then meets our qualifications for the general power rule. We have a quantity to a power, which is what the u to the n meant. And then we have after that the derivative of the u, and then the very end is dx. So what we know then is that the antiderivative for this will be that same quantity, don't change the quantity at all, raise it to the power of n plus 1, so because our n was originally 3, our new power becomes 4, and then put it over that new power. If you want to, you could write this as 1/4 x squared plus 3 to the 4th. Either one is fine, and then we have to have the plus c on the end. On example B, we have the integral of the quantity 3x minus x cubed squared times the quantity of 3 minus 3x squared dx. What you look for is your quantity to the power, that is the 3x minus x cubed being raised to the second power. Check and see if what comes after it is the derivative of the inside. Is 3 minus 3x squared the derivative of 3x minus x cubed? Yes, it is. So this meets our general power rule. Because we meet the power rule, then our answer will be the original quantity raised to a power. We're going to keep that. So it'll be the 3x minus x cubed. Our power in the integral was 2, so we're going to go up by 1 to 3 and put that over 3 plus our c. If you want to, but you don't have to, you can write this as 1/3 times the quantity of 3x minus x cubed to the third power plus c.